In this video, we're going to look at selecting motors based on torque and speed needs for the joints in a serial manipulator. Today, we will account for only two factors in calculating the torque requirements. First, angular acceleration of the links. Second, gravity on the robot payload and on the links themselves. Let's start by looking at the most simple case. A motor attached to a link so that the direction of motion of the link is perpendicular to gravity, as I've shown here. In this case, our torque needs don't depend on gravity at all because the direction of gravity is always perpendicular to the direction of motion. So we could write our torque needs for this case as torque is equal to I times alpha. I is the mass moment of inertia, which is defined as the integral of the mass times the square of the distance of the mass from the point it is rotating around. But it's easiest to get a feel for this by looking up some equations and doing a couple of calculations. So let's do a couple of calculations. First, let's figure out our mass moment of inertia. The motor itself has some inertia that will be quoted in the motor data sheet. And if the amount of inertia of the motor is significant, you have to account for it here. Since the angular acceleration of the rod and the angular acceleration of the motor shaft is going to be the same, since the motor shaft is coupled to the rod, we can lump together the inertia of the rod and the inertia of the motor. If we look up the mass moment of inertia of a rod rotating around one of its ends, we see that it is ml squared over 3. For now, I'm going to leave m and l as variables. To complete this calculation, we need to figure out the acceleration. Here's one common way to do that. Suppose that for our application, we need this link to rotate between 0 degrees and 90 degrees, and that the link has to stop moving in both positions. This is a common case for applications like pick and place. Now we specify how much time we will allow for this motion to take place. In this case, let's just suppose that we want to complete this 90-degree move in a half a second. To figure out the amount of acceleration needed to complete this kind of motion, I'm going to draw a plot of time on the x-axis and rotational velocity omega in units of radians per second on the y-axis. I know that the motion is going to start at time equals 0 seconds, and I want the motion to be completed at 0.5 seconds. The reason I've drawn the y-axis as being the rotational velocity is because from a plot of rotational velocity, I can get both the acceleration and the displacement, or the amount of distance moved during this move. The displacement will be the area underneath the curve that I draw here, and the acceleration is going to be the slope of this curve. Now, the velocity during this move could take any shape. I could have a velocity that goes like this, or I could have a velocity that goes like this. Any kind of shape of velocity is possible. But if I want to minimize the required acceleration in order to minimize the amount of torque that I need, the minimum acceleration move will consist of a constant slope up to a point and then a constant slope back down in such a way that halfway here is the peak velocity. This kind of a move will give me my minimum acceleration. Now I'll call this peak point omega max. From this plot, we can figure out the amount of acceleration given the amount of distance that I need to move. The distance is the area underneath this curve. I can calculate the area under this curve as the base times the height. Since we said this motion had to be 90 degrees, this has to be equal to pi over 2. So omega max is pi radians per second. Given that omega max is pi radians per second, can we figure out alpha for this move? We know that the motor has to accelerate from omega equals 0 to omega equals omega max in a time equal to 0.25 seconds. Now that we have alpha, we can plug this back into our equation to get the total amount of torque. Let's substitute in some values for mass and length of the rod. Suppose that the rod has a length of 1/2 meter, and suppose that the mass of this rod is 1 kilogram. This gives us a torque of about 1.047, and we need to take a moment to think about our units to figure out what the units should be here. Altogether, we have kilogram, meters squared per seconds squared. We also have radians here, but radians is often considered to be unitless, so we can ignore our radians. Now, we know that force is mass times acceleration, and so the units on force might be something like kilograms meters per second squared. In fact, this unit is a Newton. So if I cross off my kilograms seconds squared and one of the meters, that becomes newtons. So the units of torque that I've just calculated here is Newton meters. So how hard would it be to find a motor with this amount of torque? Let's take a look at some motors. Here I am at a website called Payload that sells many different kinds of motors, and they're well documented. Let's take a look at one of these categories of motors. Here we have a set of motors with different gearboxes where they've given the no load speed and the stall torque listed here. The stall torque is given in units of ounce inches. So first, let's convert our 1 Newton meter of required torque to ounce inches. 1 Newton meter is approximately 140 ounce inches. So if we look at this list of motors, we can see that a number of them have more than 140 ounce inches of stall torque. Now, the temptation is to, at this point, just pick one of these motors that has more than 140 ounce inches of stall torque. But this will not be correct, and here's why. If we look back at our plot of time and rotational velocity, we see that we need to exert this amount of torque. Remember, torque is the slope of this velocity time curve. We need to exert this amount of torque at all of the speeds during this entire move. The stall torque of a motor is the amount of torque that that motor can exert when the speed is equal to 0. For our application, we need the motor to be able to exert the 140 ounce inches of torque at all of these speeds, including omega max. We need to pick a motor for which the speed, omega max, and the torque, 140 ounce inches, falls below the torque speed curve for the motor. So let's look back again at our motors. We know that none of the motors with less than 140 ounce inches of torque will work. So let's pick one of these that has more, and let's see if the motor will actually work for our needs. Let's pick the motor with 57 RPM and 200 ounce-inches of torque. Here we'll draw out the torque speed curve of the motor. The no-load speed was 57 RPM, and the stall torque was 200 ounce-inches. We don't actually know what path this line takes between the stall torque and the no-load speed, but it's safe to assume it's a straight line because it won't be less than a straight line, although it might be more. The amount of torque that we need is 140 ounce-inches. But at what speed do we need this torque? Omega max we calculated to be pi radians per second. In our torque speed curve, we've made speed be RPM, so we need to convert this radians per second into revolutions per minute. This speed is 30 RPM. Back in our torque speed curve, we now know that we need the point 140 ounce-inches and 30 RPM to be underneath this curve. But in this case, this point is so close to the line, I can't tell by eye whether the point is above or below. Let's do some calculations to figure it out. We could write this torque speed curve using y equals mx plus b. Y is the torque. M is the slope of this line. X is the speed. And b is the y-intercept. The y-intercept is the same thing here as the stall torque. So, how much torque do I have when the speed is 30? We have 94.7 ounce-inches of torque, but we need to have 140. So this motor is not going to work for our application. Back in Payload, we can select a different class of motors and see if a slightly higher power motor would work for us. Let's do this calculation again with the new values. This motor will work, but the amount of torque that it has is so close to the required amount that we need, we probably wouldn't actually pick this motor. Remember that we did not account for the inertia of the motor itself in these calculations. Also, we haven't yet accounted for any kind of payload that the robot might be holding. So in general, once we calculate the torque at the required speed and find a motor that will work, we want to overspec the motor at least a little bit to account for inaccuracies in our calculations. Next, let's complicate this situation a little bit. This time, we're going to take our rotational joint and we'll position it like this. This is more complicated because now we have to consider the effect of gravity. Here, we have torque due to the acceleration of the link, but we also have torque due to the force of gravity. Here, I'm using the variable r to represent the distance from the center of rotation to the center of mass of the link. If the link has a distribution of mass that is equal, we can approximate r as being L over 2, that is half the link length of this link. We might do that in order to agree with our use of the variable L in our calculations of the mass moment of inertia. If the mass of the link is not evenly distributed, then you can't assume that R is equal to L over 2. You would have to calculate the center of mass of the link. Now, note that this multiplication here is actually the cross product. In other words, we only want to calculate the portion of this force that is parallel to the direction of motion of the link. In this position that I've drawn it here, the entire force of gravity is parallel to the direction of motion. At any instant in time, we could calculate just that portion of the force that is parallel to the direction of motion by using the cosine. Let's figure out how much more torque we would need in our motor if our manipulator was set up so that the motion was in this direction instead of in the direction shown in the last calculation. The force of gravity is the mass times the acceleration of gravity. And here I'll use L over 2 as the distance between the axis of rotation and the center of mass of the link. For the cosine of theta, since we're calculating the torque requirements for the motor, we have to calculate the torque requirements in the worst case scenario. The worst case scenario is the position that we actually drew the link and joint in the picture. In that case, the cosine of theta is 1. In our previous calculation, we assumed that the mass of the link was 1 kilogram. The acceleration of gravity is about 9.81 meters per second squared. And we had also assumed that the length of the link was 1/2 meter. So the amount of torque required to move the link against gravity is 2.45 Newton meters, or about 347 ounce-inches. So note that the amount of torque in this case required due to the force of gravity is much greater than the amount of torque that was required just due to the acceleration. Of course, this won't always be the case. If we had assumed a much greater value of required acceleration, then that source of torque requirement would have dominated. However, this explains the reason why the SCARA type manipulator is often used for pick-and-place operations. The amount of torque required to move links and payloads in a direction that is perpendicular to gravity is much less than the amount of torque required to move objects in a direction that is parallel to gravity. The total amount of torque that we need in order to move the link against gravity is the combined amount of the two torques. So we have 140 ounce-inches required to move the link at our specified amount of acceleration, and we have about 347 ounce-inches required to move the link against gravity. So for this application, we would need to spec a motor that is capable of 487 ounce-inches of torque. Before we finish today, let's go back and look at one more complication of this setup. Let's suppose that our manipulator is holding some object as a payload in its end effector. We refer to any object that the manipulator is going to be moving around as a payload. What is the effect of this payload in the amount of torque required by our motor? In this first setup, the only effect of the payload comes in when we're calculating the mass moment of inertia. The inertia due to the link does not change, but now we have some inertia due to the payload as well. It's often safe to assume that a payload is a point mass. Now, if your payload has some complicated or large geometry, then you will not be able to assume that the payload is a point mass. You have to take into account the shape of the object. In that case, you could use a theorem known as the parallel axis theorem to take the known moment of inertia around the payload's center of mass, and then extend the axis of rotation back to the axis of rotation of the joint using the parallel axis theorem. We won't be doing that in this video, but that's how you could do it if the payload could not be simplified as a point mass. If you can simplify the payload as a point mass, we can calculate its moment of inertia as the mass times the distance squared. The distance here is L, assuming that the payload is located at the end of the link. And this mass here is the mass of the payload, not the mass of the link. Note that if the mass of the payload is the same as the mass of the link, the amount of torque required to accelerate the payload is actually 3 times the amount of torque that is required to accelerate the link. Let's do those calculations. Back here was where we calculated the torque required to accelerate just the link. This time I'm going to add on 1 kilogram, which we're assuming is the mass of the payload, times the link length, which is 0.5 meters squared. Let's recalculate the torque, assuming that we also have the payload. Approximately 560 ounce-inches. So you can see that the effect of the payload is very significant. Next, let's consider the effect of the payload in this case. Here, we have to add on the force of gravity on the payload as well. The distance here is not L over 2, but it's actually L, the length of the link. Since L is 0.5 meter, we can plug that in here. So the torque required due to gravity with the payload is about 7.355 Newton meters, or about 1,041 ounce-inches. So with the payload, what's the total amount of torque that we need for this second setup? The torque in this case is equal to 560, the total torque required to accelerate the link and the mass, plus 1,041 ounce-inches, the amount of torque required to counteract gravity. So we calculated that the total amount of torque required to move the 1 kilogram link around was 487 ounce-inches, and the total amount of torque required to move both the link and the payload was 1,601 ounce-inches. So you can see that the effect of the payload is really significant. Even though the mass of the payload in these calculations was the same as the mass of the link, the effect of the payload was greater than the effect of the link. In all of these examples, we've considered only a single link in our manipulator. We could expand these calculations to also consider the effects on this joint of the next joint that is attached in our serial linkage. But that's a topic for another day, and we're going to stop here for today.